Good afternoon, everybody, and welcome to our next session of the Demo Day, Educational Demo Day, organized by the Quantum Flagship and for the QTEdu community. And today we are very happy to welcome Nico Klein from Qutools, and he will be presenting us their new experimental educational boards, which is an experiment with NV centers and an experiment for entanglement detection. Nico, please, the stage is yours.
Yeah, hello everyone. This is Nico from Qtools. Thank you, Oksana, for the nice introduction, and also thank you for the opportunity to speak here today. And thank every one of you as well for tuning in, and I hope you're having a great day today, and greetings to all of you. So as you can see, I'm here with a demo system of our latest educational development. Basically, it's the QEDU series, and it consists of one control unit, the QEDU itself, and then different optical boards that you can connect to it and that you can control with the control unit. I do have a few slides today that I want to show you, but probably I'll go very quickly through the slides, and then we'll concentrate more on an actual live demo of the systems, and I'll share the screen of the control unit for you to actually see what is happening the best. So first of all, I will give a short introduction on Qtools and on our efforts to help building a new quantum workforce for the future. And I'll talk a little bit about the physical systems that we employ. So here's a photonic system, and then one system with NV centers as well. And then show you the features of the QEDU control unit, afterwards the entanglement demonstrator, the photonic system, and in the end also the NV center setup. In between the slides, I will change to the actual demo of the devices, and I will switch back accordingly depending on how it's going. So let's see how this works. I'll start the presentation. So I have to share the screen, I guess. How do I do that? It's here. So you should be able to see the screen, but not me anymore. And
that's how it works.
See me soon as well. So now I hope you see me again.
Yes.
All right, that's great. So let's just get started with the slides. So first, a little bit of history. As I said, I don't want to bore you with a lot of details. So I do it also mainly for the recording. So if you have any questions later on, you can always go back and have a look at the slides if the info is there as well. So Qtools was actually founded in 2005 as a spin-off company from Harald Weinfurter's group at the LMU in Munich. And the goal was to develop tools for quantum physics research. And also the very first product of Qtools was a time tagger, QTOW, with which you were able to detect and compute the signals from a photonic detector, for example. But very soon, however, we also specialized in developing tools for quantum education, since we realized that for the future workforce, it is just necessary to have a better quantum physics education with actual hands-on experience for the pupils, for the students. This first entanglement demonstrator in 2008, it was still built on a usual optical breadboard, and it was basically only usable by physicists with experience in the field in the beginning, since you had to tinker a lot and to align a lot, and you had to know what you were doing. But since then, we've constantly redeveloped the system. We've cooperated with our partners that I will talk about soon to make it manufacturable in a small series. And this is like the QED that you probably know, most of you. And we've also redeveloped the source into the quantum coffer, and we've started with NV centers. And then today we are where we are now with our new QEDU turnkey quantum kit with the QEDU control unit and the different optical boards that you can connect to it. Basically, we want to broaden the spectrum of people that have to do with quantum. And we want to not only physicists be able to do the experiments and gain the experience, but also from other engineering fields to be able to make some real quantum experiments, to earn some real quantum experience in order to build a kind of quantum intuition or get a generation of quantum natives, so to speak, that can work intuitively with quantum systems. That's also the philosophy. You can see a little bit more about the philosophy of our quantum education part on this slide. And how are we going to achieve this goal of getting younger students, younger pupils go to high schools, getting them into contact with quantum systems? How do we do this? Basically, we decided on concentrating on the device itself mainly. So we're building real cool hardware, really stable. It's manufactured completely, so you get the complete system. You don't have to build it up yourself. You can just take it out of the box, take it onto a usual office desk like the one I have here, and basically start experimenting with it. In order to make this start as easy as possible, we provide a graphical user interface, basically with a guided mode included that will lead you through the experiments and show you only the parameters that are important at this stage, at this moment for this experiment, and kind of hide the rest a little bit. You can still access them in the GUI, but you can let yourself be guided by these experiment after experiment things. You'll see it later as well. We do also provide training for our devices, of course. And then there's another thing that we added lately, which is a kind of open source slice in here, which means we provide a versatile API with a Python interface, complete with open source examples. And this way, all of you, all of the community, we want to tap into your experience to take advantage of this and let you be able to also realize your own vision of how to teach quantum with our devices. So our hope is that we can tap into this and create a community in the end to share on a GitHub platform, to share their open source ideas, their code, and to make this kind of exchange between users possible as well. So the idea is we manufacture the devices, but you are the educators, and you can contribute to the actual educational didactical idea of how to teach quantum best, I think. And at this point, also, I want to thank our partners. First, we have Enhance, which is an engineering company, and also MIT, which is a manufacturing company. And with those two companies backing us, we can really make all of this possible and get the devices to you in a timely manner as well. All of these companies are actually privately owned by the same family, so we can work very closely together. And also, all of us, we are based in Germany, so all of our devices will be made in Germany and fulfill the highest quality standards, of course. So let me talk a little bit about the quantum systems that we employ in our devices. So on the one side, we have the photonic systems, which can provide entanglement. Here, usually we employ a pump laser, a very high power pump laser that is focused onto a pair of BBO crystals, which constitutes an SPDC source, so a spontaneous parametric down conversion, which is happening at the BBO crystal. So at this nonlinear optical crystal, there's a chance that one of the pump photons is going to be down converted into two photons, into a photon pair. And this photon pair is exiting the BBO under a certain angle. So we can collect it with optical fibers, with a fiber coupler in the end. And if we make everything right, and we add these pre and post compensation crystals as well, then we have an entangled state in the end, an entangled Bell state. This is, and with this entangled Bell state, you can then make different experiments. So this would be the photonic system. And then on the other hand, there's the NV centers. Here we employ nitrogen vacancy centers, which means that inside of a diamond lattice, you have, instead of a carbon atom, you have a nitrogen atom. And at the neighboring lattice side, you have a vacancy, an empty lattice side. And this nitrogen vacancy center it constitutes kind of an artificial molecule that's sitting inside of the diamond lattice and that is protected by the diamond lattice. So the big advantage of this system is that you don't need a vacuum to have it stay in place, and you don't need a cryo to cool it down to very low temperatures. Basically, you can operate it at room temperature and at ambient conditions, just in air, because everything is sitting inside of the diamond that you can glue in place somewhere. And additionally, this nitrogen vacancy center, as an artificial molecule, it shows a lot of the properties of atoms and molecules that you also see in atomic physics. So you have a kind of energy level structure that you can see here. And basically, we use a green laser to excite the system, and we're observing red fluorescent light that is emitted by the NV centers here. And then the cool thing is that the ground state is split because of spin. So we have an MS0 state, and we have MS-1 and MS+1. And the plus and -1 states are shifted according to an external magnetic field. And if we take one of them, so also these MS+ and -1 states, they are called dark states because the fluorescence will be darker a little bit. So basically, if we excite the system here with a microwave, you need a microwave for this at 2.87 gigahertz approximately, then we're going to see a change in intensity of the fluorescence when we shine a laser on it. And this we can detect and kind of use for quantum sensing, or also as a basic building block for a quantum computer, where you can learn about the different methods to coherently control a qubit. So this is what we do with the NV centers. And with this, let's just start with our devices and what is happening here. So as I've told you before, the QEDU series, it consists of one control unit, which is like this. It's handheld. You can transport it easily. You can just put it on the desk. And then in addition to this, you need a few connections to an optical breadboard. In this case here, I have the NV depicted. And you can see that the connections are very easy. You just have one data cable that also supplies the power to the experiment board. And then you have the optical fibers that go back into the control unit for the signals to be detected in the end. And the interesting thing here is that we have one and the same control unit, and it will work with both the NV system and with the photonic system. So you can connect both of them to the same unit. You just have to make sure that the detectors are fit for the job. So more about the control unit. You can see it here from the back and side, and you see it has the big touch panel for one thing, and also these wheels that you can see here, they are motorized control wheels, and you can basically take any parameter that you want to change and put it also on one of the wheels, just to have a more direct control over the parameter and change it. Or you can just use the touch panel and change everything here and observe the results on the big display as well. On the back side, we have up to 4 optical inputs, fiber inputs, that lead to our APD module inside, which is the detection module for all the experiments. And basically, these APDs, they can be either worked in a single photon detection mode, so we can detect single photons for the photonic experiment, but we can also employ them as a fast photodiode as well, which we use for the NV center setup, since there we get a lot of light because we have a lot of NV centers. So these are the 2 modes of the detectors inside the control unit. Here you can see a screenshot of the software options that you have. Basically, on the left side, you see our graphical user interface that is running on the screen of the QEDU on the touch display, which is also touch optimized. And on the right side, you see an example of a Python interface for the NV center setup, where you can see a lot of parameters and you can change them and everything. And this is what you could also by yourself, you could adapt, you can change, you can customize it. So it exactly suits your needs, basically. With this control unit, we have to control something, and here the optical boards come into play. Let me start with the ED part, with the entanglement demonstrator. Basically, the main block this is made of is the SPDC source, which you can see in the big part here. I'm sure you are familiar with this, or let's ask me some questions afterwards. But basically, here what we changed from the previous version of the QED is that we introduced two motors into this. One, we motorized the wave plate, which controls the pump laser polarization. So with this precise control of the pump laser polarization, you can basically change the kind of state that you want to produce. You can go for an entangled state by pumping with plus or minus 45-degree polarized light in order to activate both BBO crystal halves. Or you can use only vertically polarized pump light or only horizontally polarized pump light in order to have only one of the crystals active and only produce a product state of photon pairs, with which you can also make a lot of experiments. And the second change is this motorized Evo crystal that we have here, which is tiltable, so it gets kind of larger and thinner in the beam path, which means that I can precisely control the phase between the H and the V part in the produced states. This source block, it sits inside of this orange laser safety cover on the complete board, which means that you can operate this outside of the lab as well. You can operate this in a classroom, in an office, wherever you like. And basically no dangerous laser light will come out, since we have a long pass filter in the front here, which only lets through the down-converted photons and not the pump laser light. These down-converted photons are emitted under an angle of about 3 degrees. They are reflected at two mirrors over here. And then we have this free space beam path where you can put in some optical components to make whatever experiment you would like directly with the photons. And afterwards, they are coupled into a fiber with fiber couplers at the bottom here. And you can connect these fibers directly to the control unit. Or also we have, at the moment, we have up to 5 add-ons that you can add in between the fibers here or into the beam path over there to make a huge range of experiments possible in the end. So with this short introduction, let me switch to the live part of the demo, and let's see how this will work out in reality. So let me switch my camera first. It's here. So basically now you see a camera view from the back side. So when we have a look from the top again, down here I have a second camera, and it will look from the back side towards the two polarizers that are mounted at the moment and towards the fiber couplers. So you can just see directly the beam path and what is going on over there. And then I'm going to share also a different screen, where I now put the software of the QEDU unit, the screen of the QEDU unit, and allow us to actually see what is going on. I have connected this with my laptop with the VNC protocol right now, but you can also directly access this with the browser as well, and control it via browser too. As long as the control unit and my laptop are in the same network, this is not a problem. Okay, so what do we see here? First of all, on the startup screen, you can see a schematic of the control unit and also of the board that is connected to it, or in this case, the two boards that are connected to it. So here we see the entanglement part, and I have also connected the NV part that you can see here, and I can switch between the two, and I will get the different controls for the two setups. Then you see on the top, you see a kind of menu bar. Here you have all the different experiments that you can make, which is kind of the guided mode that I spoke before. And then on the bottom side, we have on the left side some general information about the system, and on the right side, all of the different parameters and actuators that I can control in the device. And I can go through here to control everything freely and as I want to. And I can go through the menu buttons on the top, through the experiments, in order to use the guided mode and let me kind of let us be led through the different experiments also in order to get everything to work. So here the first three are kind of experiments to get to know the device in order to learn about the detectors and what we can do and the different parameters and so on. And then the last two will be real quantum experiments where we will see the nature of the entanglement as well. So what do we see here in this first experiment? It's called single beam alignment. So we're looking at each of the beams separately. Here we have detector 1 and detector 2. And in this graph, it's a count rate over time. So we have now a little bit above 100,000 counts per second for the one channel and 170,000 counts for the other one per second. And you can see here the laser is already switched on at 80% around right now. And you can check that it's real by just introducing a kind of beam block in one of the devices. And at the same time, you're going to see the count rate of the corresponding channel drop. So on this side, we have channel 2. And on this side, we have channel 1. And also, you see here on the right side, we can control some polarization stuff in order to make some simple polarization experiments in order to get to know the polarizers and the half-wave plate and the source and how they are controlled and how they work together. Then in the second panel, we kind of have now we do photon pair alignment. So since now we just had the single photon beams, one on each side, and we looked at them independently. But at the end, we want to make the experiments with the photon pairs that are produced by the source. So what do we have to do? We have to make sure that we know which events of the detectors actually correspond to a pair and which do not. And how do we do this? Basically, since we know the pairs are created at the same time and at the same location, we know that they should arrive at the same time at the detectors and that the detection events should happen at the same time. And what we see here is a time difference histogram. So you see a time difference on the x-axis, and then again number of counts on the y-axis. And you see here that we have a kind of distribution around 0, and I can add an electronic delay to one of the channels to shift this in time. You can see it's happening in real time. So I'm actually receiving new data all the time, and I can during that I can in real time basically I can change parameters and I can see the result immediately. So let me just center this around 0, and then also I can control the coincidence window and say, look at this. If I go towards a small area in this small time difference between the two events like this. So now we have a coincidence window of 500 picoseconds in each direction. And we only use these events as a coincidence because we know they are very probable to come from a pair. It's very, very, very seldom possible that we have an accidental coincidence from some room light or whatever to actually happen in this small amount of time. 500 picoseconds is really, really short. And this is how we define coincidences and a pair detection. And then in the next one, you see again the count rate over time graphs, but this time it's 3 of them. And on the top and on the bottom, you still have the single count rates. And in the middle, you have the coincidences now. So these events that happen during this short time interval that I showed you before. Again, we can change the pump laser polarization. Now we can also change the EVO settings, because the goal of this experiment is to get to the best possible entanglement. And basically what you want to do is you can check for correlations. You can see I can with these buttons I can quickly control the two motors. You can see them turning in the video, I hope. And I can set them to horizontal, both of them, or to vertical, both of them, or to plus 45 degrees or some other combination, plus minus, for example, and so on. And the interesting thing to see here is that not very surprisingly, I have a lot of HH coincidences and I have a lot of VV coincidences. but I have very, very little. You see the coincidence count rate dropping here in the middle. Very, very little coincidences when I set one polarizer to horizontal and one to vertical. This is just because of how the photons are produced. And also at the same time, we have very little VH photons, which is just the other way around. It's symmetrical, right? So this is not very surprising. But then we can also look at this in the other basis, not in the HV basis, but now in the plus-minus basis, which is plus 45 degrees is one basis vector and minus 45 degrees is the other one. And then for the two qubits, we have plus plus, minus minus, plus minus, and minus plus. And the surprising thing here is that now we also see the great correlations for plus plus and minus minus configurations, but we see very little coincidences in the plus minus and minus plus space. And if you just make the calculations individually and say, okay, I'm having HH photons and I'm having VV photons, this is what I produce with the source, then you can't predict this outcome. Since then you should have also a lot of PM coincidences and a lot of MP coincidences. So this is already an indicator of good entanglement in our source. And to show you the entanglement even further, I can switch to the next display, which is called graphic entanglement, because here we have a kind of graphical representation of these nonlinear correlations that we just saw. So as a display, we have a polar diagram on the left side. As an angle of this polar diagram, I plot directly the angle of one of the polarizers, and as a radius, I use the count rate that was recorded at this angle. And I use the coincidence count rate because, again, we want to look only at the pairs. So what I'm going to do here is I'm going to set one of the polarizers into motion, and it's going to rotate continuously. And I can control the other one with the manual controls over here. And you can see if I set this second polarizer to horizontal, then I see that I have this kind of peanut structure that is emerging here, or this figure of 8, so to speak, in the software that is that has an axis that is also horizontal. So this is now because, as we've seen before, we have a good correlation between the two detections when we look at the coincidences. So now I have one motor set constantly to horizontal, and on the other side, I measure the highest count rate at horizontal and the lowest count rate at vertical. Because if I measure at the one side with the fixed polarizer, I measure horizontal light, a horizontal photon, I basically know that on the other side, I will also have a horizontal photon. And of course, this is also true if I go to a vertical orientation of the second polarizer. You can see now the axis changes to vertical. And with an entangled state, it is actually also true for the plus and minus 45 degree basis. So you can see here, I can change the polarizer also to plus 45 degrees, and I will get this maximum correlation at plus 45 degrees. I can set it to minus 45 degrees, and I get the correlation at minus 45. And the same is true for every of this angles, of this linear angles, because for the phi plus Bell state that we are producing, I actually have positive correlations in every linear basis. So I think this is a really nice experiment to kind of show how a polarization measurement will work and how the entanglement will influence the state that we are seeing here. Also, the next experiment is just a simple Bell's theorem, Bell's inequality, where we have 16 different angle settings shown here by these lines. So the dark line is always the one polarizer, the bright line is the other polarizer. And when I press play and just let this go through, I can see as a circle, I can see the count rates visualized that I measure at this configuration. And the software will automatically go through all of the 16 different settings for the Bell's inequality. And in the end, basically, the theory says that if we get to a value that's above 2, then we cannot explain this with the classical theory still using localism and realism. So there's basically quantum mechanics predicts a maximum value of 2.82. And we see here that we actually measure a Bell's value of 2.76, which is close to the theoretical maximum. And we do exclude any local realistic theory by violating this, in this case, by a lot of standard deviations. This is also really cool to see that we can make an experiment like this, where Alain Aspect in the beginning needed a whole lab to do. We can now do it on any office desk, basically, which is what fascinates me really on with this system. And then there are, of course, some more experiments that you can do, but most of them will need some kind of add-on. So let me maybe quickly go to the presentation again and show you the add-ons. Let me quickly talk about this. Video. Let me see you again. That's fine. Share the presentation. All right. Hope you're not seeing the Zoom window. So here is an overview of all the different add-ons that we have at the moment. We have up to 5 already finished and ready to be delivered. And we are working on a few more at the moment, just to expand everything all the time. We want to expand the range of experiments that you can do. We want to improve on the experiments that we already know you can do. And there's a constant development going on, since we're a development company, basically. So what do we already have? We have the Michelson interferometer, which is basically for showing interference effects, just like with the double slit. We added some polarizers into the mix to realize quantum eraser experiments, and you can also show non-interactive measurements with this device. Then we have the Hong-Ou-Mandel 2-photon interferometer that you can see on the top here, where you can observe the purely quantum effect of 2-photon interference. Basically, this effect is used and leads up to Bell state measurements and also the basics of dense coding and so on. And with our add-on, you can do all these experiments and learn about this. Then there's the HBT add-on, which introduces a fiber-based beam splitter, with which you can show that the photon will not be divided by a beam splitter and will exhibit particle-like behavior and go in only one exit at a time. And you can also show that the source produces heralded single photons and measure a G2 function, for example. Then there's the tomography add-on, which introduces quarter wave plates, so you can completely determine the state of the produced photons, and you can fully characterize this quantum state and see how it would look in the density matrix formalism, and also observe how an entangled state would differ from a non-entangled one in the density matrix formalism. And then we, of course, have a QKD add-on, where you can perform where you can show the workings of popular QKD algorithms like the BB84, and also entanglement-based protocols like the Eckert E91 protocol, where you actually use the entanglement, and Alice and Bob are kind of using an entangled source to produce correlated randomness for their key to do the secure communications. Yes, that's it about the add-ons for now. Let me just continue with the QEDNV, which is now the second physical system. So now we're not talking about the photons anymore. We take a step back. This is a different board. Now we use the NV centers, the other physical system. Because with the photons, we can show the entanglement very nicely, and the polarization properties, and how to work with photonic qubits. But there's also some limitations, like we cannot see a time evolution. We can measure the photon and then it's gone. So it's a little bit difficult as well with the photons. So here, this one is a little bit more in the direction of quantum sensing on the one hand, and quantum computation on the other hand, because with all the quantum computing physical systems that we see emerging at the moment, it's basically always the same principles with which you control these qubits. You have a pump laser to excite the system. You have a microwave to drive some level transitions, energy level transitions inside of the system. And you read it out with lasers again and detect some kind of fluorescence light from the system. And all this is happening with the NV as well. Yes.
As the time has got over 2:30, I would only like to interrupt you for a short while to invite the participants write their questions in the chat if they already have some about your first system, and we will ask them at the end of the session.
Okay. Yes, for sure. I mean, I will just quickly go over this, and then we can go to the questions. And if we have some time, we can have a look at how this actually works. But otherwise, all of you, of course, are also invited to just contact us, and we can schedule a kind of meeting, and I can show you then. So no worries if we don't have time to look at this system actually. So what do we have here? The components of the NV center setup are, as I've told you before, is a laser that comes in. It comes in here through a fiber, and it is reflected on this dichroic mirror into a microscope objective that sits here. And inside of this cage structure that you see here, there is the diamond. So inside of this cage, you see the diamond and the and also inside is the microwave antenna that we need for the microwave transitions. And this cage is constituted of the magnetic field coil, so we can precisely control the ambient magnetic field around our NV centers. Actually, we have 3 different diamonds with NV centers, so you can have a little selection and kind of compare between the different diamonds and how they differ. And in order to align everything and to select one of these diamonds, we have a 2D stage that moves both the diamonds on the stage, but also the microwave antenna, so everything is aligned correctly. And basically the fluorescent light, it will be collected by the objective again, will be emitted here, will pass through the dichroic mirror, through some filters, and be coupled into a multimode fiber here at the end as well. And this fiber will then lead to the control unit again in order for the signal to be detected. Yes, I think that's it for the NV Center. So thank you already for this, and don't hesitate to check out our website and contact us via the email address. And I hope I'll see some of you again at some time. And I think with that, we can continue with the questions and then see if we have time to have a look at the NV Center setup as well.
Okay, great, Nico. Thank you very much for the presentation. And yes, I welcome participants to write questions in the chat or raise your hand and ask, as we are not many today. And I will start in the meantime, melting the ice by asking whether with these new kits you already had some use cases, and what are the feedbacks that are coming through. Like, for example, it could be interesting to know how long are the classes that run with your setups, and what are the challenges and that the pupils and educators face.
Basically, we get a lot of positive feedback from educators, from professors all around the world. I mean, we have the previous systems already, and also for those, we get a lot of feedback. And basically what people are saying is that for a typical lab course, you have up to 4 students at a system, and usually 3 is better. So not too many at one system. So probably to get a whole lab course, you need multiple systems to have them work at all the different experiments. And then they really like the kind of combination of the basic systems with the different add-ons. So they can, for the different stations, they can build up like the basic experiment with the entanglement experiment that I showed you just now. You can have it as a first station, and then people would rotate, and they would work again with the same system, but with an additional add-on on another effect, on another observation, and they can kind of they don't need as much time to get used to the system, since they already worked with it before at another station. And this is like one of the feedbacks that we get. And the other one is that that people find it really nice that we now have in the newer system, we have these possibilities inside of the source, of the photon source itself, to control both the half-wave plate and the Evo crystal, just so we have a little bit more control over the state that we are producing, right? I think this is the main things for the photonic system. For the NV system, the feedback is that people think it's really nice to have such a compact setup. They don't have to align for a long time. Basically, with this, we have the motorized stages. So you also can do a 2D scan and just have a look at where your diamonds are. You can then zoom in and do a finer scan of the details, and you just pinpoint the location with the highest signal, and you go there and you can start experimenting, and the software will lead you through it and take care of most of the parameters for you. So you have a kind of starting point to experiment, and then change stuff from there. So people really like the transportability, the robustness, and the kind of flexibility with the different add-ons.
Okay. Thanks a lot. And just as a matter of, we've got a first question in the chat. Do you have prepared laboratory instructions, manuals that students follow? And do they have some data analysis and post-processing in form of lab report?
Yes, for sure. Let me maybe share my screen again, and then I can show you, actually. So... where's Zoom? So let me just open up our manuals. They are also on the website. And you can see here for the entanglement, for the photonic system, for example, this is the table of contents. So besides the usual like safety instructions and some technical data on the device, we have a huge section on installation, starting up, and the first alignment after transportation. And then also for each of the experiments that I just went through, we have some kind of material, which consists of a theory part. It's usually very short and to the point, because we think you can better provide the rest. But as a starting point, you have this. And then also there's an experimental description and what you can change everywhere, and what the procedure is for the experiment. And then we also provide some kind of worksheet where you can directly give out to your students if you want. And they have some questions that they can answer and fill out. And we hope they're going to learn something with it. And then also we have some kind of sample solution, which is password protected on the website. So you as an educator, you have access to it. You can have a look at this. But students, they can't download it just by Googling it, for example, and know the solution, right? And we have this for basically all the experiments that we supply in the GUI, of course. And then in the future, we do hope that maybe in this open source idea, that there's also going to be some material from the different customers. We're at the moment also in this year of quantum context. We're starting a lot of collaborations with different customers from us, and some of them will also produce some kind of material, and we can maybe set this up on GitHub as well, so you can profit also from the other customers' experiences, I would say. Thanks.
Great, thank you very much for showing the material. And we've got another question, and Madhav Gupta is curious if the nanodiamond sample can be changed by the students or users of your experiment. It would be interesting to compare the spin properties.
Yes. Yes,
Or
we realize that.
Time of different samples.
Sorry?
No.
It's actually not intended in the version that I have here. With this version, we have the diamonds fixed inside. I think it might be possible to do some kind of exchange there, but it's going to be a little bit difficult. We are working on a future version where we have this functionality as well, so you can easily switch out samples and stuff like this. Right now we don't have it, since it's a delicate combination of the microwave antenna that sits in there, and actually on top of the microwave antenna we have the nano diamonds. In our case it's micro diamonds. Actually they are comparatively big, so we also have NV center as ensembles, so we have a lot of NV centers and not only a single one in this setup. So we collect a lot of light and we can quickly make experiments and not have to wait for a long time in order to get the results and integrate over a long time as we would have to with a single NV center. So it's intended for the future. With this version, it's going to be a little bit of customization and manual things that we would have to talk about. If you really need this in a kind of collaboration, we could probably do something.
Okay, you mentioned that there are already 3 crystals in there, right?
Yes, we have 3 diamonds, but all of them are these micro diamonds. So basically what changes is kind of the how many NV centers there are, the density of NV centers, and also the orientation of these NV centers. So because they're in the lattice, you're going to see the orientation as well by tuning the magnetic field from the outside. You're going to see the different orientations shift differently with the magnetic field. So this is what you can compare between the samples.
All right. Let's see if there will be more questions regarding this part. And in the meantime, I actually wanted to ask you to say more about experiments that you offer with the NV board, as you haven't mentioned that yet.
Yes. So I'm going to share my screen again. So you're seeing the screen of the device again. And let me see you. Okay. And here is now I've activated the NV center in the software. And so you can see the experiments that we have intended in the GUI at the moment. So it also starts with a kind of alignment where you can put in a blocker and so on and see for yourself, like the fluorescent. You can see it by eye actually, because we have this ensemble of NV centers. Maybe I can show you by doing this. Turning on the laser, you're going to see the intensity of the green reference light and also of the red photodiode. And you can, here is the scan window that I was talking about. So here you can perform a scan. We're going to introduce some kind of pulsing as well. So you can see pulse sequences, since for all of the more advanced experiments with the NV center, you're going to need laser pulses, you're going to need microwave pulses, and you're going to need to observe the signal at exactly the right time. And all of this can be shown also in the bottom here. So you see kind of a typical sequence that is constituted of several laser pulses, of a microwave pulse maybe, and we have some kind of detection window, which is now the purple area. And you can observe this window for all of the different experiments. And a lot of the parameters are preset by pressing this play button on each of the experiments. And so this is the kind of the first three, again, just like in the other one, are to get to know the device and the different parameters that you can set, like the laser, and all of this is real time as well, of course. So for example, if I open the specific parameters for the laser here, for example, you see the start of the pulse 1, and I can shift this, and you can directly see in the measurement results that this laser pulse is shifted in time as well. And if we do everything correctly here, we want this to go there and start at 0. And then we can continue with the other experiments. So here we have a kind of magnetometry experiment, which is an ODMR scan, basically. So we scan the microwave frequency over the different frequencies, and we're going to observe the dark state, which you can see here. It goes down like this. Let me switch off the fans as well, so we can get a little bit less fluctuations. And you can see here, this is also being updated in real time. And what we can do actually is here we can change the magnetic field. And if I do this, I can directly observe the Z-man effect, where we see the two energy levels split and go apart with the rising magnetic field. And we can do this in X and Y and Z direction to split up the energy levels even more. So it's not very greatly aligned here. Maybe I could do a little bit better on that. But basically, we can use this for quantum sensing here, make a kind of fit. So all of these things, we can save the plot data. We can directly extract the data with a USB stick, or with by remotely connecting to the device and saving the data directly to our laptop. And then you can use Python or MATLAB or whatever to further analyze the results that you got. And also here, we can use kind of measurement sliders to measure the exact locations of these peaks, like this. We're going to see the difference in frequency between the different dips. And we can use one of them to continue our experiments and use them as a working point. We just click the button, and then we are fine to do the next experiments. And what we have here is still two more into the direction of qubit control, which is kind of a spin nutation. So now we see a kind of the laser is always on, but we pulse the microwave, and we now see the influence of the microwave on the system. So here it's going to be switched on, and then you see what happens, and you see this kind of fluctuation here. So the microwave starts to drive the transition between the MS0 and the MS-1 state in this case. And the system is beginning to fluctuate between these states, but very quickly, because the laser is always on, it's going to decohere, and you're not going to see the oscillation anymore. If you want to see the oscillation, you have to go to a Rabi oscillation experiment, which we have here as well, which uses a different pulse sequence, where basically you have the initialization laser pulse, then you have a microwave pulse that you change in length, and then you have the readout pulse at the end to read out the results. And you can also see here if this that this microwave pulse is going to be changed during the experiment, and is going to be longer and longer and longer and longer. And always at the end of the microwave pulse, I'm going to detect the state of the system. And then if I do this, I'm actually going to see something like this. We can fine tune a little bit here with the detection window. So this has to be at the exact same spot. And of course, you have to select the correct microwave frequency for this. So let's see if we get a few nice oscillations here. You can see 2 or 3 now. Sometimes you can see more. It depends a little bit on the fine tuning. And then you already see this takes a little bit longer, because now we have to do this pulse sequence. For every point here, we have to do a pulse sequence and integrate over it. And this way it takes a little bit longer, and I can introduce a little bit more averaging here. And then we're going to see kind of the Rabi oscillation of the system, which is determining in the end the length of the microwave pulses that I need to precisely control the spin of the qubit. So if I want to initialize in a kind of superposition, I will need a pi-half pulse, which means that I will go on the middle of this flank here and use a microwave pulse of this length to after the initialization laser pulse. So I'm going to initialize with the laser, I'm going to use the microwave pulse, and then I can continue. And here we're just not finished yet with all the software features. So this is also where you come in, and you can introduce your own Python software and so on. But also we're probably going to add it to the GUI as well, some more parameters, some more experiments like a spin echo or yeah, something like this with more sophisticated pulse sequences, basically. Okay, now we had the small demonstration as well. So thanks for the question here.
Okay. Very nice. Thank you, Nico, for the demo and for the presentation of your new tools. And thank you, the participants, for their questions and for following the demo day. I think we are perfectly in time for closing the session and looking forward for the next one, which will actually also be dedicated to the kit used for sensing.
All right, so have a nice day, everyone. And I hope to see you again sometime.